Page 35, number 23. Then we'll find the general solution, the solution that satisfies simultaneously the given condition which x is equal to negative 1, y is equal to 1, and x is equal to 1, y is equal to negative 1. So, multiplying both sides by this given equation by 1 over x dx, we obtain dy over dx plus x squared minus dy over x equals to 0, and this is equals to dy over dx plus x minus dy over x equals to 0. Now this is a linear differential equation, so we'll find the integrating factor, which is so the integrating factor is b equals to x to the negative 3. Now multiplying the equation with the integrating factor, 1 over x cubed, you obtain b dx. And this is equals to integrating both sides, we find that y over x cubed is equals to x to the negative 1 plus constant. Now this is the general solution for this differential equation. Now we will find the constant which will satisfy the given simultaneously the given equation, a given condition that at x is equals to negative 1, y is equals to 1, y equals to negative 1. So after we find this, y over x cubed is equals to 1 over x plus c, that is equals to y is equals to x squared plus x cubed. We'll find the constant. So first, at x equals to negative 1, y would be equals to 1. So we have 1 is equals to negative 1 squared plus c negative 1 cubed, and 1 is equals to 1 minus c. So we find that c is 0. So we have this at y is equals to negative 1 and y is equals to 1. The solution will be y is equals to x squared. Now, for x is equals to 1 and y is equals to negative 1, we have negative 1 is equals to 1 squared plus c1 squared of cube. We have negative 1 is equals to 1 plus c. We have that c is equals to negative 2. So the equation, the general solution, the solution for this given condition will be y is equals to x squared plus minus 2x cubed. So the problem is you will find a solution that would simultaneously satisfy this given condition. So we can write these two functions. So this is y is equals to first x squared and x squared minus 2x cubed. But we'll give the condition. So this condition y is equal to x squared, this would satisfy if and only if x must be less than or greater than 0. And this solution, this must be x greater than or equal to 0. So this is now the final solution. This condition and this function would satisfy the given condition from the differential equation given. But the problem is we are given this differential equation and we will solve that will find an equation that will satisfy this. First this and second is this. So in order to find the solution of this, we must find the general solution. So this is a separable equation, so separate it. This is dy over y minus 1 equals to d dx over x. And by integrating both sides, find ln 1 y minus 1 equals to 3 ln of x. And the constant of integration, this can be ln of c. By law of logarithm, this is ln of x cubed times c, and this is same y minus 1. So this is now equals to y minus 1 equals to x cubed minus c. We now find the general solution x cubed times c plus 1. So this is will be our key to find this solution that will satisfy this and this. So first we will see this. At y is equals to 3, we have x is equals to 1. Substituting this in this, we have 3 is equals to 1 cube c plus 1. This is 3 minus 1, so this is 2 equals to c. We find that c is equals to 2. And substituting this c in this, we have at y is equals to 3 and x equals to 1, we have y is equals to x cubed x2 plus 1. For the solution of this, y is equal to 2x cubed plus 1. Now for this given situation, at y is equal to 9, we have x is equal to 2. So the same process, substitute y as 9 and x is equal to 2 cube c plus 1. We find 9 minus 1 is equal to 8c. And we find that c is equal to 1. So substituting this again, this we have y is equal to 9 and x is equal to 2. Y is equal to x cubed times 1 plus 1. This is the equation that will satisfy this. Again, we'll repeat the process. This and this. Find their solution. Respective solution. Now, at y is equal to 3, it is given that x is equal to negative 1. So again, same process. 3 is equal to negative 1 cubed c plus 1. We have 3 is equal to negative c plus 1. So we have c must be equals to negative 2. Then we now have the c. So at y is equals to 3 and x equals to 1, we have y is equals to negative 2 x cubed plus 1. So we now have this solution of this condition. Now for this condition, we'll again substitute the boundary to find a solution. So it is given that at y is equals to 9, we have x is equals to 2. So again, this will substitute 9 is equals to 2 cube c plus 1. Find that 9 is equals to 8 c plus 1. So we have c must be 1 in order to satisfy this. So we now have the solution at y is equals to 9 and x equals to 2. Y is equals to x cubed plus 1. This is now the solution. Page 32, number 31. So we will prove that dy over dx, this equation ax plus by plus c over this can be transformed into a homogeneous form if and only if this a times b is not equal to a times b small, where we will going to introduce h and k, in which the relation h and k to the variables is y is equal to u plus h and h is equal to b plus k. So we prove this. So solution. Dy over dx equals to a times our x is b plus k, b plus k, b plus k plus b times u plus h plus c over a times b plus k plus b over b plus plus B given C. And since y is equal to u plus h and x equals to b plus k, it's right to say that du over dv is equals to dy over dx. We have a times b plus a times k plus b times u plus b times h plus c equals to a times b plus a times k plus b times u plus b times h plus b times c. So, in order to arrive at an equation which is a homogeneous, this is already an homogeneous equation. Since our homogeneous is, we have in the form, if you want to show that this equation will transform into an homogeneous, which is in the form of du or dv, these constants, a times a and h times b, must be equal to the negative c, so that we will arrive at the equation that is in the form a b plus bu over a b plus bu. But first, we must find these constants, k and h, in order to validate this equation, because there will be a restriction for this. We want to show this. So first, we will set this, and this, a times a plus b times h. This must be equal to negative c, and a times a plus b times h. This must be equal to negative c b. In order for this to arrive, we will solve for the values of h and k. So namely, we can use this as equation 1 and this is equation 2. And solving for k at equation 1, we get that k is equals to negative c minus ph over a. And substituting this to the equation 2, we have a equals minus c minus ph over a plus b h equals to negative c b. Multiplying this equation with small a, now to simplify, we get a times negative c times ph plus a ph this is equal to negative c times a. So we have this equation of this. We have negative AC minus ABH plus ABH is equal to negative CA. So factoring the H or solving for H, we have H negative AB plus AB. We have AC minus BCA. Solving for H, we have H is equal to AC minus CA over A times B minus AB. Okay, we got this argument that A and B must not be equal because if these two are equal, we cannot get our constant H, and as a consequence, we cannot also get our constant K. So, because A and B are not equal, we can find K and transform the equation this into the previous equation, which is in the form du over dv is possible A times x equals to b plus b plus h plus c. And since we already showed that this constant A times K plus B times H is equal to the negative of this, we can cancel it out and make this equation become A times B plus B times Q over A times B plus B times Q. We already find our goal that we already showed that this equation is possible since A times B is not equal to A times B small, which is a homogeneous equation. Now we'll proceed through the letter B. In the case of letter B, A times B is equal to B, A times B. So it is clearly that we cannot find the H, can't find H. So we'll introduce another variable, which is in the form U is equals to A times X plus B times Y, and B is equals to negative, and so on. So do something. dy over dx is equals to ax plus by is equals to u. So we have u as c, and the other one ax plus by is equals to b plus c. But our problem is the variables are dy and dx. So we must find a way in such a way that there are only two variables in order to solve. Since this is going to happen, Since we are given that u is equals to ax times by, we can integrate this with respect to x. So we have d dx is equals to a plus b dy over dx. So we have this, and transforming this will become d over dx minus a is equals to b times dy over dx. Dividing both sides by b, we find that 1 over b times du over dx minus a over b is equals to dy over dx. And we will plug in this value of dy over dx to this equation. We find that 1 over b du over dx minus a over b. This is equals to u plus c over b plus c. But we have a problem. B, there is b. We must transform this b into either a function of x or u. So we'll use this. We are given that b is equals to ax plus by. And using this equation, we can call this equation 1 and this equation as equation 2. Eliminating for y, for this, we will first eliminate y in this equation which is given, so that we can plug in the y in terms of a and x, u and x, so that we can find the b. So now we have the function of b as a function of u and x. So we have from equation 2, u minus ax is equals to y over b. Note this is from equation 2. And substituting this equation 2 to the equation 1, we find that b is equals to ax plus b times the value of y, which is u minus ax over b. Multiplying both sides by b, we find that dt is equals to a bx plus b times u minus ax. We have b equals to a times x. Distributing this b, we find it as b minus a big letter x. We will factor this x. We have x times a, big letter a times small letter b, minus small letter a times big letter b, plus b equals to bb. And since we're given of the argument that a times b is equals to a times b, we can cancel out this 4. It becomes 0. So from this, we get the relation that B times B is simply big letter B times U. This is our key to transform this equation into a homogeneous. I mean separable. Third equation is separable. So we have 1 for B. From this, 1 over B, du over dx is equals to minus a over b is equals to u plus c over. Substituting this p, we have b is equals to big letter B over B times u. So we have big letter B times u over B plus big letter C. Now, it's clearly that we can do something this way. It would turn into a separable equation. Just simply multiply both sides by b. We have du over dx minus b is equals to du plus dc over du over b plus c. Again, multiplying this by a factor of p over b, we get du over dx. So there is first this equation. So we have du is equals to b squared u plus b squared c over b times u plus b times c and plus a, and multiplying this by factor of b times u plus b times c, b times u plus b times c.
Problem number 5 of page 35. We
We
got
got
du
du
minus
over dx
x plus 1 dx is equal to 0.
equals
So we
to
can make this equation into a linear differential equation.
du plus dc b squared u plus b squared c plus a times b times u plus b times c. So this is clearly a separable equation because at this time this is already a function of u.
We got the problem x
And
y minus 2xy minus x plus 1 dx is equal to
We
0.
already found that
We can
this
make this
equation can be
into a
transformed into a
linear
separable.
differential form.
If we have given the condition that a times b is equals to a times b, I mean small letter b,
Where
a times big letter b is equals to big letter a
minus
times small letter b.
xy minus x.
Problem 38, page 38, number 26. We're given that y is equals to x times y prime minus 4 times y prime cubed. So we will find its general solution. So first, we can differentiate both sides. So we have y prime is equals, with respect to x, this is x times y prime plus y prime minus 12 y prime squared times y prime prime. So we can cancel out this. Find that y prime prime times x minus 12 times y prime squared is equals to 0. So from this, we have y prime is equals to 0. This is only implying that y prime must be equal to some sort of constant. So we have, and also this we have x must be equals to 12 times y prime squared. We observe that there is two roots for the equation, so expected that there are a lot of general functions that would yield this. So we have y prime is equals to constant. So bringing back this y prime is equals to constant to this, we have to find that y is equals to x times some sort of constant minus 4 times constant cube. So this is going to be our first solution for the general equation. And we find, and for this, x equals to 12 y prime squared, we find that x over 12 is equals to y prime squared. So we have this y prime is equal to square root of x over square root of 12, which is equals to square root of 3. And this is implying that this is dy over dx. So we find by integrating, we find that y must be the integral of this 1 over 2 square root of 3. This must be plus minus because there are two roots, plus minus x to the 1 half dx. So we find that this y is equals to plus minus 1 over 2 square root of 3 x to the 3 halves over 3 halves and plus some sort of constant c. Cancel this, cancel out this. And we find that y must be equal to x to the 3 halves over 3 square root of 3 plus c. This will be plus minus. So this is now the equation. Y is equals to plus minus x to the 3 half over 3 square root of 3, and also this. These two functions must satisfy this general equation. Must satisfy this differential equation. Page 56, number 29. So in the problem, it is stated that the rate which the reactant is consumed must be proportional to the concentration, which at its concentration at that time. So we can have this the rate, the concentration which consumed. This must be equal to Kc. But we already know that the constant must be a negative because the rate is in a decreasing form. So we have dc is equals to negative Kc dt. Or we have dc over c is equals to negative K dt. So we found that ln of c must be equals to negative K. And we let our constant d, can have this d. So we have c must be equal to a to negative K plus d. So we can write this c equals to a to the negative K times e to the d. But e to the d is also constant, so we can make it d prime e to the negative 3e. But we are given that at initial condition, in which at time is equal to 0, we find out that the concentration is equal to C. So we have C must be equal to D prime e to the negative 3. And since at t is equal to 0, t is equal to 0. So CO, so we have d prime e to the 0 is equal to 1. We found out that d prime must be equal to 0. So putting back this d prime equal to 0 in this equation, we found the general solution for the consumption of the chemical into this becomes CO e to the negative 3t. This solution would satisfy this differential equation.